So yeah, we're really good at graphing those inverse functions, but what about the derivatives? And I just want to show you something over here, right? Let's have a look at this. This is just a very basic example. We've got linear functions that I've got the inverse of. So for example, I've got y equals to 3x plus 3 and its inverse function there. I've just rearranged it so that y is the subject. And have a look here and see if there's a relationship between the gradients of these two, right? And I guess the linear function is not particularly interesting because with a linear function, the slope is always the same. But we can see that the slope is 3 and the slope is 1 and 3 in this one. But let's take a look at this one over here. This one's a little bit more interesting because now I've got y equals to x squared and y equals to the square root of x. These are the inverses of each other, assuming that I restrict the domain so that x is greater than 0, right? So if I look at these two here, and now it's a little bit more interesting. For example, this one here is 2, and then it's half on the inverse. So q is the inverse, p is the original. And as you move it around, I wonder if you can see any points that may be interesting. Let's go to a nice whole number and see what we can get. So let's try to get to 3. And now when you look at 3, we've got the slope of the inverse. Its corresponding point being 0.3 recurring. Now those numbers may jump out to you, but let's have a look at this. So we've got the original function and we've got the inverse and we have, let's look at the gradients m. So for example, the first one we looked at, the original was 2 and this gradient was half. This one here was 3 and this one is 0.3 or 1 and 3, right? And we can sort of confirm our suspicions by choosing another point. Like if I go down to, try to get to 4 maybe. If I zoom out a bit, there we go. 4 and our slope is 0.25 or a quarter. So hopefully you can see that that when I look at the gradient of the original function, its corresponding point on the inverse, its gradient ends up being the reciprocal. And we shouldn't be particularly surprised by this because, for example, what is our formula for gradient? We know that in general, our formula for a gradient, for a linear function at least, is something like this, right? So the rise over 1. And if you're swapping them, if you're swapping corresponding x and y values, you're going to get something like this. You're literally just going to be taking the reciprocal there, right? So that's kind of the relationship that exists between these original and inverses. But what I want to focus on is I want to look at finding the gradients of these inverse functions, because that's particularly interesting in the sense that, like, let's for example, I have something like this. So here's our first example. Let's say we've got f of x is equal to x cubed, right? Now to write the inverse, we should be clear. I know that we can just swap x and y values, keep in mind that f of x is y, but we should keep in mind that you're actually creating a new function here. So we should sort of explain what we're doing, right? So I should say for the inverse function, swap x, y values, right? And what's that going to give me? Well, then I'm going to get x cubed, x is equal to y cubed if I swap them. Now, we can't just stop there because typically for the inverse function, we also want to make y the subject. So an extra step that I'm going to do here now is I'm going to say, all right, well, y then would be equal to, how can I remove this cube from this side? Well, I can cube root both sides. That's also the equivalent of saying x to the power 1 on 3, right? And then now I can find the derivative of this. So that's dy dx is equal to 1 on 3 x to the negative 2 on 3 when you subtract 1 to the power and bring the coefficient down, okay? So that's all well and good. We can do that pretty easily. I'm going to give you another one just to check this, right? So I can give you something like this, for example. Right, and the way I can do that is I can say, all right, so I've got now x is equal to y minus 3 all cubed. But now I want to actually think about, okay, I want to make y the subject here. So I'll do the same thing as I did before. Even though I've got these brackets here, it doesn't affect anything because I can still operate them in the same way. So I've got x to the power 1 and 3 is equal to y minus 3. And I can add 3 to both sides and get my inverse function there. Again, I want to take the derivative, so kind of a similar thing that I've got here actually. So it's going to be 1 and 3 x to negative 2 and 3. And the 3's going away. That's not a particularly interesting thing. So here's another example, slightly different one now. I've got a 5 to the power. Just sort of keeping in mind, when you've got an odd power there, it actually works out quite nicely when you find the inverse, because you don't have to worry about those positive and negative cases. But same idea, for the inverse, we're going to swap x, y values, right? And so what I'm going to do then is I'm going to say, okay, well, I'll swap them and I'll get x is equal to y minus 3 to the power 5. I can take the fifth root of both sides here, so that's also the same as writing x to the power 1 and 5. And then I can rearrange for y as the subject here. So I'm going to get y is equal to x to the 1 and 5 plus 3. And I'll take the derivative as I was expecting to do. Should be negative 4 and 5 there, to take away 1. But, and the 3 will go away. But what I want to highlight is, okay, sometimes this isn't going to be the preferred method. For example, let me give you something like this. Let me give you this function here. Now let me highlight why it's not the preferred method. Because if we do the same set, so swap x and y values for the inverse, what you're going to find is, okay, I'll swap them around, but remember, what was the next kind of crucial step we had to do? Not only did we have to try and swap these values, we needed to make y the subject. And my question is this, how can we make y the subject here? Well, in fact, it's quite difficult. I'm not even sure if it's possible, to be honest, because you've got this y cubed here. You've also got this e to the y here, which you want to make the subject, and it's not really going to work. So we sort of need an alternate method. And the alternate method relies on a little sort of algebraic trick with the chain, man, can I say something? Chain rule, right? So we know that when we sort of start looking at the chain rule, we got something like this. So that dx dy times dy dx is equal to 1. That was like a little trick we could use. We're going to rely on this trick again simply by rearranging. We're going to say that dx or dy dx rather is the same as 1 over dx dy. Okay, so why does this little kind of algebraic trick help us? Because what it allows us to do is, what does dx dy actually mean? Well, I mean, to think about that, go back to what dy dx actually means. What dy dx is you're taking something with y as a subject and differentiating with respect to x. And in the same way here, if I want to find dx dy, what I can do is, okay, well dx dy, I've got x as a subject, I've got y's over here. And so I can actually find dx dy in this way. So dx dy will be equal to, now just be careful here because you are going to have to use product rule because you've got two functions multiplied together, right? But when we do that, I'm going to get 3y squared. It's interesting because I've got e to the y here, so that'll make things quite nice and easy, wouldn't it? So that's me using product rule. What that means though is, right, I've got dx dy. That's actually not what I'm looking for though. I'm just going to factorize this out actually first so I can take out y squared, so I should get left with something like this, okay? What does this help me do? Well, what's dy dx equal to? Dy dx is equal to 1 over dxy. These are sort of equivalent expressions. And the whole goal of this was that I could find dy dx, right? So what is dy dx? Well, dy dx is the same as 1 over dx dy. And conveniently, we do have dx dy. It's just this expression here, right? So I can just substitute that in as it is. Now, one thing you may notice is that, okay, what's different about this expression compared to the previous ones? Well, the previous ones were in terms of x. This one is in terms of y. And so that's potentially something that may be a bit different. But what you'll tend to find is, and the questions I'll show you later on, is that that's okay. Because typically they want you to find the gradient at a particular point. And if you want to find the gradient at a particular point, rather than substituting the x values now, you're just going to be substituting the y values for something like this, okay? So that's how that might be different, okay? So that's our first look at finding derivatives of inverse functions.